Welcome back to the deep dive. Today we are looking at a really fundamental architectural choice in AI development.
Right. How do you give an AI agent a memory? A real persistent memory.
And we're digging into a GitHub repository for a project that takes a radically new approach. It's called Memvid.
It's one of those projects that it doesn't just try to improve a system. It feels like it's trying to just delete the entire category of infrastructure that we've built up around this problem.
Exactly. The problem being how to create reliable, long-term, and fast memory for large language models.
Which is a massive engineering challenge.
Absolutely. So our mission for this deep dive is to really understand Memvid's core claim.
Which is a big one.
It is. They say they can replace the entire complex stack we use for this stuff. I'm talking retrieval augmented generation, RAG pipelines, the whole ecosystem.
All the server-based vector databases that go with them.
All of it, and replace it with basically a single file.
That's the promise. And you have to understand, today's RAG pipelines are, well, they're heavy, they can be brittle, and they are definitely expensive.
So Memvid comes in and offers this idea of persistent, versioned, portable memory that's completely infrastructure-free.
No servers, no complex deployment scripts, just instant high-performance memory in one package.
Okay, before we get to how they do it, let's just sit with the pain point for a second. To someone new to this, a RAG setup might seem logical, if a bit complicated. Why is it such a headache for the people actually building these things?
Well, think about a typical enterprise RAG pipeline. It's not just one database.
Right.
You've got your raw data storage, maybe S3 buckets. Then you need an indexing service to chunk that data. Then you need a separate embedding service to turn those chunks into vectors.
And then the core of it, a high-performance, server-based vector database like a Pinecone or a Qdrant to actually store and search those vectors.
And all of those pieces have to talk to each other. They need to be kept in sync, monitored constantly.
It sounds like a distributed systems nightmare.
It often is. You're managing schema changes, dealing with latency between the raw data and the vector index, and trying to prevent semantic drift, where the index gets subtly out of sync with the source. It's a mess.
So the problem is cost, complexity, latency. And Memvid's answer is to just put it all in one file.
That's the idea.
Let's start there then. This portable capsule, what is it?
Okay, so at its core, Memvid is a portable AI memory system, and its whole purpose is to solve that sprawl by creating a self-contained unit, or capsule.
Instead of the data being in one place, the embedding somewhere else, the search index on another server.
Requiring network calls, auth checks, all that latency. Yes, Memvid flips that entirely.
How?
It packages 4 critical things into one single file. They call it a capsule context, and it has a .mv2 extension.
Those 4 things are?
The raw data itself, the vector embeddings for that data, the optimized search structure, so all the indices, and all the necessary metadata.
So the AI agent, instead of calling out to a remote server, just opens a local file. The file is the memory.
That is the entire paradigm shift. It becomes infrastructure-free. It becomes model-agnostic. The agent can be on a desktop, a server, an edge device, and it carries its entire history with it.
Like giving it its own brain in a box.
Exactly. And because the search structures are right there in the file, retrieval is basically local memory access. It's not a slow network transaction.
Okay, this is the part of the repo that I found really, really surprising. The inspiration here isn't from database design. It's from video encoding.
I know. It's a brilliant conceptual leap.
Why are they building a rewindable AI memory timeline using ideas from, like, video codecs?
It's all about integrity and density. Video encoding is just hyper-optimized for storing huge amounts of sequential data frames efficiently and, crucially, immutably.
So Memvid just translates that concept over to AI memory.
Right. Memory is organized as an append-only, ultra-efficient sequence of smart frames.
Let's define that. What is a smart frame?
It's the basic, indivisible unit of knowledge. It stores the content, sure, a document, a line of dialogue, but it also stores a timestamp, a cryptographic checksum for integrity, and other metadata.
And by committing memory as a sequence of these frames, you get some big advantages.
Huge advantages. And that phrase, ultra-efficient, that ties right back to the video concept. They're using compression techniques adapted from codecs that are built for sequential data.
So the file can get very large but stay dense.
Exactly. But the real engineering win here goes way beyond just file size.
What are those key benefits for an AI?
First and foremost is data integrity.
Hmm.
The memory is strictly append only. You never go back and change or corrupt existing data.
So if you need to correct a fact,
You just append a new frame that supersedes the old one. The past is locked in, preserved.
and I'm guessing that immutability is the key to crash safety.
It is. Frames are committed one by one. If the system crashes mid-write, the timeline is perfectly fine up to the last fully committed frame. There's no corruption.
Because you can't corrupt the past, you can perfectly rewind it.
Okay.
Which brings us to this idea of a rewindable memory timeline.
Exactly. This isn't a static knowledge base anymore. It's a dynamic, auditable timeline of how the AI's knowledge evolved. That's critical for building AI systems you can actually trust and debug.
Okay, let's move into some of the advanced concepts that make this timeline real. Because this isn't just a fancy log file, it's a living memory engine.
It is. That's the core system that lets an agent continuously add to its memory, branch it, evolve it over days or weeks. You don't need a big database migration every time the knowledge changes. The engine just appends new frames.
And this leads to my favorite feature name from the docs, time travel debugging.
It's a great name.
It's a huge deal for anyone who's ever tried to figure out why an agent went off the rails.
Oh, absolutely. Think about the utility. Your financial agent made a bad trade yesterday. Before, you'd be digging through a mess of different logs and database snapshots.
A total nightmare.
Now, you can literally rewind the .mv2 file to its exact state from Monday morning, replay the workflow, and see precisely what knowledge it had when it made that bad call.
It makes the whole thing auditable by design. That is a massive deal for enterprise use.
Huge.
But wait, if we're packing all this data and 3 separate indexes into one file, doesn't search slow to a crawl? They claim crazy speed with Smart Recall.
They do. They're claiming sub 5 millisecond local memory access.
Ow.
It's not about brute force, it's about locality and intelligence. Because the structure is append only, the system can use really effective predictive caching. It anticipates what data the agent might need next and pulls those frames into memory before they're even asked for.
So it's a totally different world from waiting on a network round trip to some remote database.
Completely different. And there's also something they call codec intelligence.
What does that mean? The file optimizes itself.
That's basically it. It borrows from media codecs and can auto-select and even upgrade its own compression techniques as the file grows. The capsule stays efficient over time without a developer having to manually reindex or tune a database.
So let's make this practical. I'm an engineer. What can I build with this that was just too hard before? What's the so what here?
The biggest thing is that it enables truly complex, stateful AI applications that were just impractical before because of latency or infrastructure costs.
And because it's model agnostic and works offline.
The possibilities get really broad.
So what are some of the use cases they highlight?
The most obvious one is for long-running AI agents. Agents that need to remember conversations and context over weeks, not just minutes. Like a personal assistant that actually remembers the details of a project from last month.
And the offline part must be huge for certain industries.
Oh, it's critical. Think of offline-first AI systems on edge devices or in secure environments where you can't have constant cloud access.
Like in defense or remote industrial sites.
Exactly. Or in specialized domains. They mention domain-specific agents for medical, legal, and financial sectors.
Where having a private, self-contained, and perfectly auditable knowledge base isn't a feature, it's a requirement.
Right. If all the knowledge is in one encrypted file, compliance and auditing become radically simpler.
And it seems pretty accessible for developers who just want to try it out.
It is. The core is written in Rust for performance Memvid core, but they provide SDKs for Node.js and Python plus CLI, so you can integrate it without having to rewrite your entire stack.
Okay, now let's really get under the hood. I want to peer inside this .mv2 file. The docs make this really bold claim.
I know the one you mean.
No, .wall, .lock, .shm, or sidecar files. Ever. That's a direct shot at traditional databases that rely on all those companion files.
Yeah.
How do they do it?
It's all about an obsessive focus on the internal file structure. They basically solve the problems those external files solve, but they do it with carefully ordered segments inside the one file.
Okay, walk us through it from the top of the file.
So it starts with a tiny 4-kilobyte header. Just has the magic number to identify the file, version info, that sort of thing.
Is this cool enough?
Right after that is the embedded wall, the write-ahead log.
Wait, but they said no walls files.
It's embedded. It's not a separate file on the disk that the OS has to manage. This internal log is their crash recovery. If a write gets interrupted, the system only has to read that small internal segment to roll back to a safe state.
That is clever. A safety net built right into the main file. So where's the actual data?
That's next. In the data segments, that's where all those compressed smart frames live. And then right after the data, you get to the magic part, the three indices that make retrieval so fast.
These are the real engine room in the file.
Absolutely. First is the Lex index. This is for full text search. It uses a Rust library called Tantivy and the BM25 ranking algorithm.
Which, for anyone listening, is the classic, powerful way to do keyword search. Find me documents with these specific terms.
Exactly. But you also need to search by concept, not just keywords. That's what the VEC index is for. It stores the vector embeddings and uses an HNSW algorithm.
Hierarchical, navigable, small worlds, which is basically a super fast way to find things that are conceptually similar, even if they use different words.
Correct. And that's often paired with ONNX to run the embedding models efficiently right there. So you have keyword search and semantic search, both local.
But what ties it back to the timeline concept?
That's the third one, the time index. It's what maintains the strict chronological order of the frames. This is the index that powers the rewind feature and the time travel debugging. It's built for time-based lookups.
And it all gets wrapped up with a footer.
A TOC, a table of contents. It's a footer that just stores the exact locations of all the other segments, so the system can jump to any part of the file instantly without scanning.
This is so much more than just a data file. It's a whole, self-contained database architecture. So what about multimodal? Agents need to see and hear, not just read text.
And that's where the feature flags and the Rust core come in. It shows the architecture was designed for this from the ground up.
So what are some of these flags?
Well, beyond the basic Lex and Vec for text, you get the really interesting ones. There's a clip feature flag.
For CLIP visual embeddings,
Yep.
so the agent can search images.
Right. You can ask your agent, find me that slide deck about Q4 marketing with the blue whale logo, and it can actually search the images in its memory based on that description.
All inside that one file.
All inside the one file. And if you enable the whisper flag, you get audio transcription. You can drop meeting recordings in, and the transcribed text becomes part of the searchable memory.
That's incredible. It's integrating multiple data pipelines into one clean system.
And there are others, like temporal track. This adds natural language date parsing, so you can search for last Tuesday's team meeting instead of a specific timestamp.
And for all those enterprise use cases, you have to talk about security.
Of course. There's an encryption flag. It enables strong, password-based encryption for the whole capsule. The file extension even changes to .mv2e to show it's protected.
This has been a really fascinating deep dive. To sum it up, Memvid seems to be fundamentally simplifying ARA and AI memory by just condensing all that server complexity into a single, portable, time travel-enabled file.
It's a compelling, decentralized alternative to the big, centralized vector database model that's dominating everything right now. It pushes the memory, the intelligence, right to the edge where the agent is.
And the whole thing is Apache 2.0 licensed, so it's wide open for people to experiment with. Which leads us to our final provocative thought.
Right. If these .mv2 files become truly self-contained, shareable artifacts with versioning, checksums, maybe even expiry dates built in, what does that enable?
What new forms of decentralized private AI knowledge sharing could emerge from that?
I mean, imagine a bank compiles an audited, encrypted financial knowledge base.
And shares it as a single .mv2e file to its partners, a file that's programmed to just expire in 6 months.
Knowledge becomes a portable version artifact, just like a piece of software. It could completely change how we manage and share intellectual property for AIs.
A verifiable, time-stamped knowledge economy built on these secure, rewindable memory files.
It's a huge shift in thinking.
Something for you to chew on until the next time we dive deep.